Do you guys know where that's from? Cool Cats and Kittens? Well, yeah. Oh, well, when you guys find out. So yeah, it's been a rough time. I actually have a whole new piece of equipment right now. So I'm actually on a Surface Pro, which the City College ordered a bunch of them so that they can give to, I guess, teachers, I guess. But here's the thing. Now, it would seem like it would be more convenient, like someone mentioned, but they actually didn't order styluses with the Pros. So it's like, I literally have the tablet hooked up to Surface. It's been crazy around here. So now I have to figure out I have a tablet hooked up to a tablet. That is how much stuff is going on around here. Yeah. I know. I'm wondering myself, like, why would you order all these surfaces and not order like any styles and not even one? I mean, I understand that it's an extra cost, but geez, if you have like 50 Surface Pros, maybe get like 10 pens, maybe a few people might use them. I don't know. What are these teachers? They expect us to type everything. But yeah. Yeah, it's silly. But it seems for now this thing is working with the, it's working, but I probably would have preferred to be able to use the Surface itself, just by itself. Until then, yeah, it's been a rough ride. So I don't know if any of you saw it, but the recording for RS2 last time did not go well. And I was blaming my tablet, but it turns out I think, which in hindsight, it makes a lot of sense. My laptop was the issue. Like, this thing is like 5 years old, and I realized that the performance is different when I'm not streaming or when I'm just using the Surface Pro. The writing thing actually goes a little better. So I think it was just the computer hardware couldn't keep up with how fast I was writing. So hopefully that's good, all taken care of now. So what I'll do is, when I'm sharing my screen, just as a precaution, I'm going to turn off my video as I'm sharing the screen, and hopefully that will let things go by a little bit smoother. So this is going to be another test run, first time this equipment, but let's get into it. I think, yeah, so no one's been logging in for a while now, so let's actually just move on. Let's share the screen here. There is Jhevon's notebook. Now, I'm hoping everyone can actually see that. Okay, cool. All right, so all right, so okay, so if everyone can see this is what we're going to go through today. We are going to start a lecture on parametric curves and their calculus, where the calculus part I'm going to kind of be rushing through, but it's important stuff nonetheless. However, some of the calculus part isn't in our syllabus, but I decided it's actually very important. I do want to mention some things to you guys, even though technically it isn't covered. A lot of it should be more straightforward once you actually figure out what a parametric curve is and how they operate. Just me showing you some formulas for the calculus should make it pretty clear. And so I'll just have you guys watch me go through some examples. But yes, today is April 6th, and this is the Math 212 section GH. So RS2 already covered this. But yeah, let's actually begin. So these guys we might be used to seeing curves in scalar form. Yeah, you are behind until tomorrow, so you'll officially catch up tomorrow, which is why it's a Wednesday schedule. So with tomorrow, you'll actually be where they are. So we're behind by one class, but it's actually not totally. It's kind of on purpose because we missed the class. So yeah, as of tomorrow, we'll catch up with the other class. Okay, so let's move on. So we're used to seeing curves in the XY plane in what we call scalar form. So this is pretty much equations as you're used to seeing them. Y equals x cubed or x squared plus y squared equals 4. This is an example of a function. That's an example of a relation. And so we kind of already know what those guys actually mean. So let me. So this would be, oh, let's see that. It's not bad. Okay, and this guy is just the equation of a circle, as you would know. All right, look at that circle. Oh, okay. I think things are a little bit better now. That alone is already past old performance. Okay, so sometimes though, what we're going to delve into now is that it's convenient sometimes for us to represent each coordinate or each variable that we're used to thinking of as functions in their own right. So sometimes we want to measure the x coordinate as a function and the y coordinate as a function, and they're kind of doing their own thing separately. And we want to actually talk about the x and y coordinate in some other variable, okay? So whenever we're doing that, so we can talk about x as a function of some variable t. We can talk about y as a function of some variable t. And in this case, the variable t is called a parameter, right? So if you have x is some function of t and y is some function of t, the variable t is called a parameter. And so the equations x of t, x equals x of t and y equals y of t, these guys are called parametric equations. And the system here, when you talk about the x equation and the y equation, and then you tell me what range of t values are valid, that thing is called a parametric curve, because you will be able to actually plot that curve. So how would you do it? Well, we're gonna get to that in a little bit. But one thing that you'll notice is that I can be on the XY plane, like so, and I can plug in a t value, one specific t value, into the x equation, another specific t value into the y equation, and then, by the way, do you guys see where my stylus is pointing, where the pointer is? Let me double check that. Nope, you can't see where the stylus is? I'm moving it around right now. Interesting. What about now? Okay, so Georgie can. You can now? Okay. All right, so what we can do is we can take a t value, we can plug it into the x, plug it into the y equation, and we'll get a point, right? And that point we'll call x of, say, some t value, t naught, and then y of, oh, we called it a. Call it a and y of a. That's the first coordinate. And then we can keep doing this to get a whole bunch of other points until we get to the final point, which is what x is going to be when we plug in the b coordinate, and y is going to be when we plug in the b coordinate. And so what we can do is we can trace out a curve here in which we can actually plot points and connect the dots kind of the same way that we did before, right? So the first point here is called the initial point, as you see me written in the definitions there. And this point here is called the final or terminal point. So we can call this the final point, or we can call this the terminal point. And then all points in between we just get from certain t values. So what we want to do here is just talk about, once we actually consider our variables in this way, consider each variable, our x and y, as functions on their own, what are some of the theoretical consequences of doing this? And why would it actually be even necessary to do this? And we're gonna slowly reveal why something like this is going to be useful. By the way, you've actually seen this before. Now, I don't know if you've realized this, but if you think of trig, right? So trigonometry, this is this whole branch of mathematics that we all know and love. I'm sure all of you love trigonometry. You all know a lot about it. But do you guys remember how trig actually came to be, right? Right? Basically what happened was we had the unit circle, right? We had the unit circle. And for some reason, we wanted to be able to talk about each coordinate on the unit circle in terms of some angle that was made with the positive x-axis. And so what we did was we used functions to actually track these coordinates, right? So we called the cosine to be the function that tracked the x coordinate, and the sine function to be the function that tracks the y coordinate. Essentially what we did was we set the x coordinate equal to the output of some function, and we set the y coordinate equal to the output of some function. And basically, through Pythagoras' theorem, we went through, and by connecting this guy straight down and forming a right triangle, we could use Pythagoras' theorem and derive all these cool things about the points along the unit circle. And that relationship between the triangle and the circle, this triangle geometry, is what formed trigonometry. Literally an entire branch of math was formed just by us doing this right here. Just by us deciding to say, okay, let's track our x, let our x and y coordinate be tracked independently using some other functions. And so theta here was called a parameter. And just by us setting up this parameter theta and tracking x and y's in terms of some other function of this new variable, we could develop an entire new area of math. And trigonometry is actually pretty darn useful. Hopefully you guys are convinced of that by now. But I just want you to appreciate that that entire branch of mathematics was simply invented by us saying, let x be this function, y be that function. And we applied it to a very specific scenario, the unit circle. Boom, we have trigonometry. What we're going to do now is we're going to look at that in a little bit more general terms. And so we are going to talk about that in general. And so what we have here is one thing I do want to define before we move on, because I'll probably be using this phrase a lot. If you look at this definition here, when you go from a scalar form of a curve to a parametric form of a curve, right? So the scalar form, remember, is just when you have it in usual XY form, right? And the parametric form is, of course, when you write it as x is its own function and y is its own function. Then if you go from this form to that form, you say you've parameterized the curve, or you can say we found a parameterization of the curve. And also something that's important, which I'll show you guys a bit later, parameterizations are not unique. They're not unique. You will have many ways to parameterize exactly the same curve. So once we go from a situation where we don't have a parameter to a situation where we do have a parameter, we call that a parameterization. Or we said we found a parameterization of the curve, or this new curve is the parameterized curve. So let's just look at parametric curves for a second, and then I'll talk about parameterizing towards the end, actually. So let's just start to get a feel for this. So here, let's look at this curve. We have x equals 2 minus t, y equals 3 plus 2t. our t value goes from 0 to 1. What I'm going to do here is I'm going to sketch the curve. I'm going to show you the two main ways in which we can do this. But just, I also want you to know, eventually, by the time you get to Calc 3 for sure, you'll be able to think in terms of parametric curves, and you won't need to really do a translation, the kind of what we're going to be doing now. So one way to actually understand a parametric curve is just bring it back to the old way of looking at things. So for example, one way is to use a table of values. And plot points, right? Now, this is very basic, very rudimentary. In fact, I don't expect any of you to actually do this, but just to show you from the basic fundamentals working our way up. So we have, let's say we have our t here, and we know that our x is just 2 minus t, and we know that our y is 3 plus 2t. And I furthermore know that my t is going to start at 0, and it will end at 1. So I can come up with a table of values. So for example, when t is 0, I plug it into the x is going to give me 2. And at the same time, if I plug it into the y is going to give me 3. So it turns out that when t is 0, the coordinate 2, 3 is on the graph. Okay, and you can actually keep doing this, right? So let's plug in 1 point here. Let's say we plug in a half, right? And so if I plug in a half for t, 2 minus a half, that is going to be 4 over 2 minus 1 over 2. This is 3 over 2. And if I plug in a half here, that would be 3 plus 1, that would be 4, right? And I can actually continue here and plug in a whole bunch of points and come up with a whole table of values, all the way going down to the end where I might have plug in 1 for t, my x will be 1, plug in 1 for t here, and my y will be 5. Okay, and so what we can do here, you'll notice, let's just do that. So now I can actually conceptualize what this guy is going to look like. So let's that be the x and y plane. So I know there's going to be a point 2, 3. That's a point here. And so this is x of 0, y of 0. Then there's another point, 1.5, 4. This is x of a half, y of a half. Then I can have another point, which is going to be 1, 5. Right, so that's 5, that's 4, and now I can connect. Hold on, my phone is. And now if we connect these points, you'll see that we have just we'll actually just get a straight line. So this is here a straight line. And so that's how we can actually have a concept of this curve. Is that clear? Any questions so far? Okay, cool. All right, so here's another way to think about it though. So that was one way to get it. Another way, a second method is going to be 2, where we eliminate the parameter. And I would say that this is the preferred method. So eliminating the parameter is another thing that can be done. What do I mean? So your x was 2 minus t, and your y was 3 plus 2t. What you could actually do is you could solve for t from the x. From this one, you can get t is equal to 2 minus x. What you can then do is you can plug this in the y equation. So y would be 3, 2, replace the t with 2 minus x. So that's 3 plus 4 minus 2x, or in other words, that's 7 minus 2x. So now I have y is 7 minus 2x. And so then I can actually figure out what this curve would actually look like. It is a curve whose y-intercept is going to be 7 and slope is going to be minus 2. Now, it is going to hit here when x is 7 over 2. But in the meantime, if I am between 1 and 2, this coordinate here, this is going to be your x of 0, y of 0. And this point here is going to be your x of 1, y of 1. And so what you can kind of do is you pretty much just ignore everyone else. Okay. Why is a straight line called a curve? That's just what it is. A straight line is just a curve that doesn't turn. A curve with constant slope is called a line. It's one of those semantic things. It's kind of like how we have a special name for a square, even though it's a rectangle. Why don't we call the square a rectangle? It's just that you want to give a certain connotation to a certain kind of curve. So curve, yes, in everyday human language, it does mean something that bends. But mathematically speaking, a curve is just a set of points that we're connecting together. If you have the set of points having constant slope, you call that curve a line, but it's still just a curve, mathematically speaking. Any questions on the method about eliminating the parameter? Okay, so far that's so good. I mean, it's technically speaking, this is a lot easier than integration, right? And series. But yeah, we are learning, we are starting things from scratch. We are developing something from the very basic foundations. Okay, so parametric equations is just, we want an equation that tracks the x and y coordinates separately. And so that will give rise to special kind of curves. Now, you notice that this curve that we drew happens to be a straight line. It's not always a straight line, but this one happens to be a straight line. One thing we can notice is that if we can eliminate the parameter, we can get it into a familiar form that we're used to, which is probably going to be the preferred method for us. So here's another example. So what if we had to sketch this? Now, what do you guys think that curve is going to look like? Well, you wouldn't think of it as a system of equations, at least not a system of equations that's linear. Most people, when they hear a system of equations, they think linear equations. It's not always going to be linear. They can have whatever in them. So in this case, you'll notice that the y has a squared term in it. Yes, no intervals. It's just a quadratic. Do you know what quadratic it is? How would you sketch it? All right. So a lot of people tell me in parabolas, no one's getting specific, but let's actually do this. What I would do here is, again, I would eliminate the parameter. Now, in general, I can use any equation. Easier to eliminate parameter here. So that's what I'm going to do. So I can get t, in this case, is going to be x minus 1 over 2. This means that my y is equal to t squared, but that is equal to, well, x minus 1 over 2 squared. And that's going to be equal to, well, 1/4 x minus 1 squared. And so that leads me to it has intercept when x equals 1, and it goes up like that. Okay, so that's the problem. And in fact, I can even solve for what this would be just by plugging in y equals 0. If your y equals 0, sorry, I can solve for this by plugging in x equals 0, and then I would get y equals 1/4. And so that would be that problem. Now, one thing I want to point out here is my phrase here. So you probably noticed, but it's also natural to associate a direction with a parametric curve. This is one of the reasons, this is a part of the charm. It's one of the reasons why that makes it a parametric curve so useful. So when someone tells you about something like, oh, y equals 7 minus 2x, sure, you might have some concept of slope, and you would know that if y is being measured as a function, this is a decreasing function. But I want you to notice here that there is a direction, a natural direction kind of built into this situation here. Notice that if I start at the initial point, I start here. I start at the x0, y0, right? So this is the initial point. But if the final point is here. So this here is initial, and this here is final. So a direction is implied. So you'll notice here that there's an implied direction here. So not only do I have a straight line, but I do notice that there's some sort of direction associated with this line. I can think of someone moving along this line in that direction, which kind of goes to show if you're in some context where a vector kind of interpretation of the world would be useful, as is in physics, as is often in engineering, etc. A parametric curve might be a lot more useful to you than just me telling you the equation of a line. Similarly here, this one will have a direction. Notice that if I plugged in, say, t equals 0, notice that if I were to plug in, say, t equals 0, I would get my x equals 1 and my y equals 0. So that would be this point over here. Now, if I were to plug in t equals 1, I would get my x equals 3 and my y equals 1, which that would be this point over here, which automatically kind of tells you that we're moving in this direction. So you can imagine that I'm traveling around this curve, but I'm going in a very specific direction, right? So there's an implied direction here. So you'll notice as t increases, we're moving to the right. Okay. So one thing that's cool about parametric equations is that you can often talk about a kind of direction that's associated with everything. So that's an important thing, and we'll get to that pretty soon as well, but that's just something else I want you guys to notice. You might also notice that there are some patterns that might emerge from this. So if your x and y are both linear equations, your parametric curve is also going to be linear. If your x is linear but your y is quadratic, notice that if you plug a linear function into any other kind of function, the second function is what's going to determine what it looks like. Also, if your x is a function of cosine and your y is a function of sine in the linear case, you will get either a circle or an ellipse, which actually brings us to the next situation that I wanted to mention here. So let's look at that situation. So let's talk about circles. This is actually an important thing that we're going to want to look at in some detail. So here's a circle. The center is h comma k with radius r. This is a standard way of parameterizing a circle. If you want to actually travel around it once, counterclockwise. This is traversed counterclockwise. And again, how would you know it's traversed counterclockwise? Well, you plug in theta values slowly increasing, and you'll realize that as you plug in values, you move in a counterclockwise fashion. Why is this the parameterization? So let's say you have here, scroll down here. Okay, so if I have something like x minus h squared plus y minus k squared equals r squared, one thing I can do is I can divide both sides by r squared, more specifically. So if we're assuming r not equals 0, it's some positive distance. And then what we have is we have something squared plus something squared equals 1. This reminds us of an identity. Namely the Pythagorean identity. If I set the inside here to look like a cosine, and I set the inside here to look like a sine, then cosine squared plus sine squared equals 1. So this means I am thinking of specifically my x minus h over r is equal to cosine theta, which of course means that my x is equal to r cosine theta plus h, and my y minus k over r is equal to sine theta, which means my y is r sine theta plus k. And so this gives a parameterization. And you will notice, for example, suppose hk is the origin. So this gives you x equals r cosine theta and y equals r sine theta is circle centered at the origin. And notice here, if we were to actually look at what this would kind of give us. So if I plug in theta equals 0, you'll notice that I would get x equals r and y equals 0. This is this point here. This is r comma 0. If I plug in, say, theta equals pi over 2, I would get that my x is equal to 0, because cosine of pi over 2 is 0, and my y is equal to r, so that would be this point up here. This is 0 comma r. So notice we're moving in this direction. So counterclockwise direction implied. Okay, so this is a standard way to parameterize a circle. It comes from us taking advantage of a trig identity, and which we all, again, remember. And so this is a standard way to parameterize a circle. That's kind of just something for you to know at this point. Now, we get an ellipse if the r for the x and y are different. Ellipse. An ellipse occurs if you have x equals, say, a cosine theta plus h, and y equals b sine theta plus k and your a not equal to b, this gives you an ellipse instead of a circle. It means that the radius along one of them will stretch farther than the radius along the other. So you get kind of this smushed circle, either in the vertical direction or the horizontal direction. Any questions so far? Well, I think I answered David's question just now by me plugging in the thetas. Yeah. So yeah, so that's why we know it goes counterclockwise. Just plugging in the theta values. As theta increases, the points move around the circle in this way. And notice here, I actually put a limit on this just so that we can actually go around the circle one time, just between 0 and 2 pi. Okay, that's it. That is, for now, all we want to know about the basics of parametric curves. Is just another way to look at curves where we track the x and y coordinates separately. And we can talk about, and I'll talk about how to go from this kind of curve to a parametric version of a curve towards the end. But as far as the basics go, what does it mean? What would it look like to draw one of these curves? How do you get points along the curve? That's pretty much all you need to know. Parameterizing circles, this is how it's done. I'll also talk about that a little bit later as well. But let's move on to calculus, because this is a calculus class after all. How would we go about actually doing calculus with parametric curves? So this is the part that, you know, I'm gonna kind of rush through, even though I'll pause for questions if you have any, because not everything here is actually super important for you to know for your syllabus. And so if any of you are in the RS2 section, I don't anticipate anything much from this section being on your final at all, but it's really actually important stuff, and I think it's a really bad idea to actually leave it out and not say anything. So here's how we're gonna do it. We're gonna use the chain rule. The chain rule is so useful for things in calculus. So many things we derived in Calc 1 because of the chain rule. So should be no surprise here that this guy makes an appearance. Correct. So I believe 11.2 is not in your syllabus, but I'm pretty sure that's a mistake. So I want to cover bases. Yeah. So here's one version of the chain rule that you guys are probably, we don't use it very often unless you want to derive something, because it's easier to work with this form to derive things. And in Calculus 3, you're going to learn a lot of things derived from this formula as well. dy dx is, we can think of that as dy du times du dx, where y is a function of x and u is some inside function, right? So if I think of we normally think of, well, if your u is an inside function, then if you were to differentiate that, this is just the derivative of the outer function, leave the inner function alone, multiply by the derivative of the inside function. Another way to write this guy is just to think of it as the derivative of y with respect to u. And another way to think of this guy is the derivative of u with respect to x. So it's pretty much the same chain rule formula that you know and love. We just write it in a nicer way. Sometimes it's going to be intuitive here for you to cancel the du's, and that's how you get the dy dx. Okay, so there are many cases in which we actually want to express the formula this way, because just mathematically it's easier to work certain things out. And that actually will help us derive a formula for the derivative with parametric equations. So if my x is x of t and my y is y of t, then my dy dx, I can think of this as dy dt times dt dx, which you might notice is that I can actually just take the dy dt on top and just flip, and this should be an x. And just flip the dx dt and put it in the bottom. And so that gives us a formula, dy dx. In other words, the first derivative in terms of the x and y coordinates will be given by the dy dt over dx dt. So that's a formula that we'd want to know. Or you can think of it as dy dt equals y prime of t over x prime of t, if understood. Pretty soon, especially when you get to Calc 3, we're going to sort of abandon more and more the prime notation because we're going to be dealing with several independent variables and it gets kind of confusing. When you write a prime, no one knows who the prime is with respect to. It gets harder the higher up you go. So we'll use gradually use more Leibniz notation. So knowing it this way is really nice. In the same way, kind of using this idea in the way that the derivative notation in the Leibniz notation is very versatile, we can figure out the second derivative by doing something that might seem very strange at first. Think of this as the derivative of the first derivative, which makes sense. But that I can actually kind of think of as the derivative of the first derivative over a small change in x. And then what I can do is I can multiply both sides by 1 over dt, which is just dividing by the small change in t. And what that would mean is, let's move this down a little bit. And what that would mean is, I would get d dt of the first derivative divided by dx dt. And that will be your second derivative. So in case you want to talk about concavity, inflection points, and all that good stuff in the parametric universe, but you want to talk about the first derivative and the second derivative in terms of the xy universe, which sometimes you might need to switch between universes, that's how you'd actually derive the formula. Now, there are some obvious things we want to mention here with slopes. You might want to know, when would you have a horizontal tangent line? This will be useful in discovering where maximums and minimums are by taking in light our definition of critical points and Fermat's theorem and all that good stuff. Also, when a vertical tangent line might arise. And so we know that when the slope is 0, we get a horizontal tangent line. But because our slope is this fraction, it's only 0 when the numerator is 0. So if we figure out where the numerator is 0, we would be able to figure out where we have horizontal tangent lines, assuming that the denominator is not 0 at the same time, because that would, of course, cause problems. Now, if your denominator is 0 and your numerator is not 0 at the same time, you get a vertical tangent line because your slope would be undefined. Now, if you're in the case that if there's a possible t value that makes both of them 0 at the same time, what you do is you kind of use limits to approach the bad value. And since the top and bottom are approaching 0, you can use L'Hopital's rule to figure out how the slope is going to behave when you approach that point. That being said, let's actually just run through some examples here. So suppose we have a parametric curve that looks like this, which is actually going to be a pretty complicated looking curve, but we will not worry about what it looks like for now. For now, what we're going to do is we're going to actually find out all this information about the curve. What does its first derivative look like? What does its second derivative look like? What are the points where the tangent line is horizontal or vertical? When is the slope 3? Find the equation of the tangent line at t equals -2. We're going to run through all of these. So let's actually do that now. So A. So we know that our x is equal to t squared minus t plus 2. Our y is equal to t cubed minus 3t. And so this means that our dx dt is going to be 2t minus 1. Our dy dt is going to be 3t squared minus 3. And so this means that our dy dx is equal to dy dt divided by dx dt. And that is our first derivative of this, this curve. Now we can go on and we can find the second derivative. We can go in and we can find the second derivative. Someone just entered the room. What we are going to do by the formula, this is actually the second derivative dy squared, dx squared. This is just d dt of the first derivative divided by dx dt. This means I'm going to take d dt of 3t squared minus 3 over 2t minus 1. And then I'm going to divide that by dx dt. So now the top, you would differentiate that using the quotient rule. So it's the bottom times the derivative of the top minus the top times the derivative of the bottom over the bottom squared over 2t minus 1. That is going to be 12t squared minus 6t minus 6t squared plus 6 all over 2t minus 1 cubed. That is going to be 6t squared minus 6t plus 6 over 2t minus 1 cubed. And that's our second derivative. Question on the first and second derivative? Okay, cool. Let's move on to the third question. Find the points where the tangent line is horizontal and vertical. So see, so for horizontal tangent line, this means your dy dt equals 0 and dx dt not equal 0. This means that we have 3t squared minus 3 equals 0, which gives us that our t is equal to plus or minus 1. And so note dx dt is not 0 when t equals plus or minus 1. So these are the guys we want. And so points for horizontal tangent, points for horizontal tangent. So remember that our, let me remind myself because I forgot myself. So when t equals 1, I get my x is equal to 2, my y is equal to minus 2. When t equals minus 1, my x is equal to 4, and my y is equal to, t equals minus 1. So that's 3 minus, that's 2. So these are the 2 points. So xy equals 2 comma minus 2, or xy equals 4 comma 2 for horizontal tangent line. And we have that. So for vertical tangent line, so for this you need dx dt equals 0, your dy dt not equals 0. So this means that your 2t minus 1 equals 0. This means that t is equal to 1/2. That's the only one. this means that your x would be equal to paste that again. This means that your x will be equal to a quarter minus a half plus 2. And so that would be minus a quarter plus 2. That's 7/2. And the y would be 1/8 minus 3/2. Or in other words, that would be 1/8 minus 12/8 minus 11/8. So this means xy equals 7/2, comma, minus 11/8 for vertical tangent. We're not going to talk about arc length right now, so let me move this out the way. Oh, that sucks. Okay. Boy. Okay, where are we? So that was C. 7/4. Yes, that should be 7/4. Okay, everything else looks good. Okay. All right, moving down. Part D, when is the slope 3? So we know from before that that's the slope. No. And from before, that's the slope. So now part D, we were asked, when is the slope 3? So if I want to find the points on this parametric curve when the slope is actually 3, what I would do is just set dy dx equals 3. So this means 3t squared minus 3 equal over 2t minus 1 equals 3. This means that 3t squared minus 3 equals 6t minus 3. This means that 3t squared equals 6t. So what are my solutions for t here? No. Remember how to solve polynomial equations. Bring everyone to one side, factor. So we have t equals 0 or t equals 2. And so, yeah, this is the when. Oftentimes, the parameter here is called t because oftentimes we're going to think of t as time. So it's not a point or a location. We can think of that as an. So when t equals 0 or t equals 2, the slope will be 3. Looking at the other one, find the tangent line when t equals -2. E. Tangent line when t equals -2. So boom, boom, boom. When t equals -2, this means that your x is going to be -2 squared minus a -2 plus 2. And so that's going to be 4 plus 2 plus 2. That's 8. And your y is going to be -2 cubed, -3 minus 2. It's going to be -8 plus 6. This is -2. So the point is going to be 8 comma -2. And the slope, well, this is dy dx when t equals -2. This is going to be 3 times -2 squared minus 3 over 2 times -2 minus 1. This is 12 minus 3, that's 9 over -5. And so this implies the tangent line you want is y minus y1 equals m x minus x1. That's our tangent line. Okay. So again, very basic stuff, but we need to know how to do the basics when we're developing a new area of math. So we're developing the parametric curves, the theory behind parametric curves, which you will continue in Calculus 3, because it's just a nice, parametric curves also provides a nicer way to look at curves in 3D, which I'll kind of start looking at with you in this class, but you'll really go to town with that in the next course. So yeah, we know what a parametric curve means, how to plot one. Now we know how to talk about calculus with it. So we can find derivatives and second derivatives and tangent lines, which, as you guys know, we can approximate curves with tangent lines. That was a big thing in Calc 1 that was emphasized. So even when a curve is very complicated, instead what you can do is you can point by point replace locations on the curve with the tangent line to the curve and use a straight line to approximate a curve at any given point. And so we can use calculus to kind of approximate curves. So knowing how to approximate tangent lines and slopes of a parametric curve is actually super useful, because parametric curves, we are going to have the ability to make things a lot more complicated and get some really crazy looking curves, which I'll probably show you guys a few in the next lecture. So knowing how to deal with things like that, super important. Another topic, arc length. So pretty much how do we measure the length of a parametric curve? And in pieces is actually the answer, spoiler alert there. So suppose I have some random curve moving in the XY plane. And so this is the X and that's the Y. and this is some curve x of t comma y of t. That's this curve. How do I know how long? Let's say I'm from this point where x of a, y of a, going all the way to this point, which let's call that x of b, y of b. So this is the curve x of t, y of t, where your t goes from between a and b. Okay. Now, what is the length of this curve? How far did I travel? If I was a little guy walking along this curve, how long would I have to walk to get from one point to the other? What is the distance traveled? Not really. So here's the calculus way of approaching things. So yes, maximum, minima, but that's not going to help us find the distance really. So here's how we're going to find the distance. Okay, so when it comes to the two kinds of thought patterns that calculus actually teaches us about, right? One of them was the dissection pattern, right? So one thing that we've learned in calculus is, like when you wanted to find the area of a curve, you kind of dice up the interval into smaller subintervals, and then you kind of find out the area on each of these subintervals and add them all up and get the aggregate. So that's going to be one way to do it. Well, a series is where it's going to start, yes. And then another way, another thing calculus teaches us about is the idea of a limit, the idea of inching close towards something. So we use the inching close towards something idea to actually develop the derivative. We use the aggregate idea and then taking an infinite limit to develop the integral. So these two methods of approach, these two problem solving techniques is what makes calculus a useful pursuit. It's one of the two main methods of breaking problems down. So that is essentially what we're going to do here. What we want to do to figure out the length is we're actually going to break this curve up into different sections. And we're going to break it up into sections on which we know the answer. So straight line segments. So I'm going to pick some points, connect it to a straight line. And then what we're going to do is the sum of the lines, sum of the length of the lines is approximately the length of the curve. And of course, the more lines, better approximation. And so we would essentially, so here's how we're going to figure out how we can actually measure this. So let's look at each line segment, right? So let's say this guy here is x1, y1, and then this guy here is x2, y2, and then this guy here is x3, y3, etc. So this we're going to move down. So here's what we're going to do. So I'm going to use I subscripts to figure out the lengths of each of these guys here. So for the ith line segment, the length of this line segment is going to be just the distance between xi minus 1, yi minus 1, and xi yi, right? So this is just the distance between two adjacent points, right? So this is like, so for example, the distance between, say, x1, y1 and x2, y2, right? So that I can call this part here. That's like my L1, right? So this here is L1, okay? So now, well, technically I kind of wrote it another way, but you guys get the idea. So technically this would be L2 by the way I labeled it. That was okay. Okay, so that's the length. Now, by the distance formula, we actually know what this is. This is just going to be the square root of the change in the x values squared plus the change in the y values squared. Now we're going to do, of course, our old math trick where we multiply and divide by a change in t over the change in t. I can bring in one of these t's inside. So this is delta x over delta t squared plus delta y over delta t squared. And I'm left with a delta t out here. And now what you can see that we're doing so this means L, which is the length of the line, is just going to be the sum over all i's of all the li's. And let I approach infinity to get the exact length. This gives you, of course, a Riemann sum. And so basically this just turns out to be the integral from the first point to the last point of x prime of t squared plus y prime of t squared dt. And so that's actually a formula that we have. So this gives us L equals the integral from a to b of the square root of x prime of t squared plus y prime of t squared dt. This is the length of x of t length of curve given by x of t, x equals x of t, y equals y of t for t goes between a and b. So that's our formula. And again, we kind of use the same sort of situation where we would figure out area to kind of find the length of the curve. What looks much nicer? The final form. Yeah, final form. Yeah, so that's the final form of the formula. And yeah, let's actually just jump right into an example. Suppose I had a parametric curve looking like this guy. And on this interval, 0 to 3. Now, don't worry about what this curve actually looks like. It's actually going to be a very complicated curve to figure out. But let's actually find the distance that we would have traveled between t equals 0 and t equals 3. So I can do the length. It is going to be equal to the integral from 0 to 3 of the square root of x prime squared plus y prime squared dt. So this is, of course, going to be e to the t minus e to the minus t. This one is going to be minus 2. So this here, this is x prime of t. This here is y prime of t. Okay, so pretty much we are going to now solve this integral to find the length of this curve. Now, of course, step 1 is to simplify. So this will be, oh my God. This will be e to the 2t minus, well, 2 plus e to the minus 2t plus this guy here is going to be 4. Which is going to be e to the 2t plus 2 plus e to the minus 2t. We'll get to that later. Okay, how would you guys do that integral? What would you substitute? And what would your du be? Brain ran out of fuel. You can actually get a u sub to work here. U sub is not necessary here. Anyone see a trick? Trig identity? Who's the trig identity? Oh, you want to write this as cosines? Now, the problem with getting cosines and sines in here, probably how you're thinking about it, is based on Euler's identity that we had before. You'd also get complex numbers getting in here. Here's a hint. Maybe this will help. Look at this guy. Look at this guy. Does that help? No, that doesn't help. I mean, think about it. What is this guy? Where did that come from? Sure, it came from the derivative of x, but what do you see it now? What is this? It's a light bulb. The light bulb went off. Right, so this came from the e to the t minus e to the minus t all squared, right? And this guy looks just like that guy, except there's a change in sign in the middle. So this guy, you can imagine, is just going to be e to the t plus e to the minus t all squared. And so now, basically this becomes the square root of e to the t plus e to the minus t all squared radical dt. Okay, and what is that? Okay, give me the technical answer here. Because it's possible for you to get in trouble. Well, we don't need a u sub. We still don't need a u sub. But the square root of this squared is not just the inside. If you take the square root of x squared, what is that? It's absolute value of x. So here, technically you want absolute values here. However, in this situation, it's not going to make a difference. But it's possible that it could have made a difference. But in this situation, of course, e to the t plus e to the minus t is positive. So the absolute value is just itself. Now, that's what the expression that you would have in here might not behave like that. So it's very important that you're careful not to put in a negative part in the answer when there should have been positive parts and all that, etc. So the square root of something squared is the absolute value, which means you might have to break up this interval, but here we don't. So this is just e to the t, e to the minus t between 0 and 3. And so this is essentially e cubed plus e to the minus 3 minus 1 plus 1. Sorry, this is minus. Yeah. So e cubed minus e to the minus 3 is going to be our answer. Right, so there's no plus c because it's the definite interval. So yeah, that is the length of the curve. If I were to travel along this curve, well, let me see something here. Hold on, I'm trying something in another window. Okay, so if you look here, there's no way I could have done this on my other laptop. So here I actually, this is the equation right here. It's actually a sideways parabola. And too bad they did. Okay, so the t range I want between 0 and 3. So that's what the graph actually looks like. It's actually the bottom half of this that we're walking along. So the length of this curve here is actually e cubed minus e to the minus 3, which is pretty cool. pretty cool that we can figure out the length of that curve. Where are we here? Oh, maybe I should, wait, do I know how to do this? Hold on. Is it Windows Shift S? All right, I'm taking a snippet of this here. And let's move over to our OneNote. And yeah, that's actually our curve here. Yeah, I know. Tell me about it. Yeah. What did this other guy look like? I don't think I put anything too crazy. Let me see, t cubed minus 3t. You guys want to see what the other curve looked like? Do another snippet here. So what this curve actually looked like, the one that we had up here, he looks like that. Yeah. So notice that here, that's a very complicated curve. So, oh, math can do a lot more than tires. Just don't worry about that. We're going to see a lot more complicated graphs than that. But one thing I want you to appreciate is that thing is not even a function. So the parametric curves that we have here, they don't even represent a function. So obviously finding dy dx would have been a problem in that situation because that curve we'd only be able to represent implicitly, not explicitly. You wouldn't be able to solve for y in this situation. But yeah, just so you know. No, which screen am I sharing right now? Let's make sure I'm sharing the right one. Okay, we're back in OneNote. Okay, so yeah, so cool stuff. All right, so the last thing I want to talk about, is that the last thing I want to talk about? Yeah, the last thing I want to talk about today. So it wasn't a very hard lecture, but it's just a new concept, new ideas that we're actually going to do a, well, you guys are going to do a lot with them. We're going to do some more with it in this class, but really it's Calc 3 is going to go off with the parametric equations, because really imagining things in 3D or higher, if you want to imagine curves in 3D or higher, parametric curves, which you can feed into vector functions, is going to be the way that you're going to want to do it. And I'll kind of show you in this class why that would be the case. But yeah, just know that this stuff is going to be useful. So while it's kind of, we're dealing with very basic things at the moment, don't let that underwhelm you. You'll get to complicated things soon enough. So don't worry about that. That being said, let's actually talk about parameterizing certain curves. This is a pretty useful thing. How would you go from a scalar version of a curve to a parametric version of a curve? So we want to parameterize things. Now there are three different categories that I want to talk about, because in a math class of Calc 2 or Calc 3 level, these are pretty much the three broad situations you would find yourselves in. So Parameterizing straight lines is going to be very useful. Being able to parameterize circles is also going to be useful, and pretty much anything else. I'm going to give you a strategy that can work with almost anything else that you would see at this level. Of course, I can't tell you everything, but I'm going to tell you some things here. So let's say you want to parameterize a straight line segment connecting 2 points. So here's a standard parameterization. So to parameterize the line segment from x1, y1 to x2, y2, we can use the formulas. We can use the system. So, x equals, you start at the initial point, then you figure out what you have to add or subtract to get to the final point. So x2 minus x1, and you multiply that by t. For the y, you do the same kind of situation. Y initial plus y final minus y initial times t. And it turns out in this situation, you will always want t to go between 0 to 1. So that is our system here. And yes, for this formula, it is always t goes from 0 to 1. For this formula, I used to teach Math 392, and then people either think that use 0 to 1 for everything, which is not true, or some people get into the other camp where it's like they never could figure out what their t values should be when they're using this formula. And I'm like, it's always 0 to 1. It's not something you have to think about. Just know that it's 0 to 1. How you can know it's 0 to 1, what you can appreciate is if I were to plug in t equals 0 here, this part will be gone and that part will be gone. And you notice that your x and y give you the x1, y1 coordinate. If, on the other hand, I'm supposed to plug in t equals 1, what would happen is the x1 and this minus x1 would cancel out, the y1 and the minus y1 would cancel out, and I'd be left with x2 and y2 respectively. So when t equals 0, it starts at the initial point, and when t equals 1, it ends up at the final point. So it's always going to be 0 to 1 for this set of forms that I can give you. And another way you can figure that out is just that here's an idea you can use. X2 minus x1, you can think of this as equals whatever you have to add or subtract to go from the initial point to the final point. Now, any of you who have experience with vectors and how they work and how you connect vector from one point to another point, this will kind of be obvious, but I just want to make sure that I'm covering all the bases here. So yeah. So for example, let's say I wanted to do this example. How do you go from parameterize the line from 1, minus 2 to 3, comma 4. So I want to go from 1, minus 2, and I want to end up at 3, comma 4. What I can do is let x equals, start at the 1, then figure out what do I have to add or subtract to go from a 1 to a 3. Clearly I have to add 2. 1 plus 2 is 3. Attach a t to the 2. Y equals, started at minus 2. What do I need to do to go from a minus 2 to a 4? Well, I need to add 6. Attach a t to the 6. And that's it. That's your parameterization. That guy would be a straight line that when t equals 0, it starts at 1, comma minus 2. And when t equals 1, it will end at 3, comma 4. Is that clear? Does everyone get that? All right, cool. That's it. That's all you need to do for a line segment. That's pretty much it. This is a standard way to do it. I do want you to appreciate that, well, I'll get to that in a little bit. Let's talk about this guy, circles. And various situations in which you might have a circle. So let's talk about the circle centered at the origin with radius 2. And I'm going to talk about various parts of this circle. So we kind of know from above, when I was talking about circles, the standard way to kind of parameterize a circle. So from above, we know that setting x equals 2 cosine t, y equals 2 sine t, and t goes from 0 to 2 pi, gives the entire circle. Your x squared plus y squared is going to be 4, which is that circle. Now, what if someone wanted something like the upper semicircle? How would you tweak your parameterization to make sure that you only get the upper semicircle? Right. So you would just, in that situation, the parameterization would be essentially the same. X equals 2 cosine t, y equals 2 sine t. But now you just bound the t differently. Your t would just go between 0 to pi, right? So you can actually bound it. So you move from 0 to pi. Or we can say the quarter circle. In second quadrant. So I'm talking about this part of the circle here. And you can say pi with the, like 4 asterisks. Yes, not PIE. Okay. So again, you can say x equals 2 cosine t, y equals 2 sine t. And what would your t bounds be here? Pi over 2 to pi. So here's another one. What if I asked you the right side of the circle? That means I want this here. Right, it's minus pi over 2 to pi over 2. So what you always want to do is you want to make sure that you go from a smaller angle to larger angle. Now, a common mistake that students would make here is that they think of this as pi over 2, and they think of this as 3 pi over 2, and they would say something like t goes from pi over 2 to 3 pi over 2, which first of all makes no sense. Well, not that it doesn't make any sense. That's not what I want to say. Which first of all, because sometimes they put all the lower one up the top, but I want you to notice what happens here is if that this is the start and that is the end, what you're going to get is it starts at pi over 2 and then goes down here. So you'll get this side if that's what you put in. And if you were to go from 3 pi over 2 to pi over 2, that's what makes no sense. If you were to say something like, for example, your t is between these two. So these here are some common errors that you would see. People either giving you the wrong part of the circle, or they're increasing, or they're moving in the, or they're writing down an inequality that doesn't make sense, because this is not actually true. It's not true that this guy is bigger than that guy. So some few things to worry about that can actually cause a lot of headaches. Be careful that you're moving from a smaller angle to a larger angle if you want to cover something counterclockwise. Here's the other thing. This is how you would do straight lines in general. This is like the brain dead way of doing a straight line. And this is, oh, before moving on to this, let me explain another thing. So, alternative to the upper semicircle. Now, if you only have the top part of a circle, one thing I want you to notice is that we can actually write an equation for that. See, with the full circle, we couldn't actually do this because you get a plus or minus when you try to solve for the y. So you have two wings, and you would have to worry about both sides. But notice what you can do here is that if you were to solve for the upper semicircle, well, let's actually talk about the next method, and then we'll go back to that, and you'll see it make a difference. So this thing here, this, you'll notice it's not a line, and it's not a circle. So it's the anything else category. So here is a standard approach, an approach that works often. In Calc 2 and Calc 3 anyway. Is to solve for all variables in terms of one variable, right? So here you only have two variables, the x and y, but in general, you go to Calc 3, you're gonna have x, y, and z. And if you're in 4 dimensions, you have like 4 different variables. Essentially, if you want to parameterize a curve, you solve for, pick one variable and solve for all the other variables in terms of that one variable. What's going to happen is that then set that variable equal to a parameter. So for example, we have the parabola y equals x squared going from 0, 0 to 2, 4, right? So this is our curve here, y equals x squared, 0, 0 to 2, 4. So we're moving in that direction, 0, 0. Here we're at 2, 4. Okay, how would you actually write that as a parametric equation? Now, one thing you wanted to notice here is that y is solved for in terms of x. So I have every variable solved for in terms of one variable. There are only two to talk about here. So this implies what I can do is I can let x equals the parameter, set x equals t. And then because y is solved for in terms of x, I can just plug that in here. And this system will describe that parabola. Now, of course, I have to put bounds on t's to get the part of the curve that I want. And who would, what would the bounds be here to get that part of the curve? Zero to 2. And why? Well, because the x is t. This means that the t values are the x values. So my x went from 0 to 2. X went from 0 to 2. So my t would also go from 0 to 2. And so this system here is a parameterized curve for the parabola y equals x squared from 0 to 2, 4. So I can go from this situation where I'm in a scalar form, and I can write it in a parametric form, where each variable is kind of doing its own thing. It's also worth pointing out that the same could be achieved by, say, something like this: x equals t cubed and y equals t to the 6. This will give the same curve. This one, though, what would happen is your thing would actually move a lot faster, right? So this is kind of a curve that's traveling along the same path, but it's actually moving faster along that path. You'll realize that your x would get from 0 to 1. Yeah, it's a curve when it's a little bit more anxious. Yes, you can kind of talk about not only a direction in which you move along the curve, but you can control the speed at which you're moving along the curve. And it might just be convenient for you to do, and here, of course, you'd let your t goes from, of course, the cube root of 0 to the cube root of 2. And so this is another parameterization, right? So this is just to remind you, parameterizations are not unique. We can vary the design to parameterizations are not unique. So here, this is the same curve, same direction, but I might want to say a different speed. Right? So yeah, curves aren't, you don't have a unique parameterization. There are times when there's a standard way to go about it because it's just easier in most cases, but there's no one way to do it. You can parameterize any curve in theory in an infinite number of ways. Now, if you go back to the upper semicircle, we already parameterized this to look like that guy with trig functions. But let's say for some reason or another, and this is something that's going to be useful to you, you didn't want to use trig functions. One option would be to solve for the y. In the case of the upper semicircle, we can solve for the y and get it as a function. Then set x equals t. And this means that your y would be equal to the square root of 4 minus t squared. Then I can let my t go between -2 and 2, and that is another way to parameterize this curve. So this is by strategy below. This here is exactly the same as the semicircle up here. It's the same curve. This one is a trig function parameterization. This one is a non-trig function parameterization. They describe exactly the same curve though. So there are cases in which this might be convenient for you to use. In particular, this might be convenient for use. In particular, if I wanted to go around the full circle, this would be a nicer function to use, where there might be times where I don't need a full circle, I only need half a circle. And so what I could do is I could just solve for this as a function, y as a function of x, and let x be as a parameter. And that can get me to the same thing as well. It can get me to the same curve that way. So yeah, so that's just, those are all slightly different concepts, but what I want you to take away from this is there's no unique way to parameterize a curve. There are some standard ways that you want to parameterize straight lines versus circles versus quote unquote anything else. And it's pretty much for the anything else category, try to solve for everybody in terms of one variable if possible, and then let that variable be the parameter. There's a little bit more to this than that, but we don't have to worry about that being, we don't have to worry about the other things until we're in more than 2 dimensions. 2 dimensions is kind of nice. But a curve is always going to be one parameter, whereas you might think of a surface, a 2D surface, there will be 2 parameters, a 3D solid would be 3 parameters, etc. But yes, being able to go from a scalar version of a curve to a parametric version of a curve is something that's going to be important in general. And these 3 scenarios are scenarios that you're going to find yourself in often. And so you'll want to know how to deal with them. Move everything up. Yeah. Gotta let what sink in. Yes. Well, as I said, I'll save these notes for you guys. You can read through slowly and make sure all the concepts actually sink. So I put a lot of notes in here so you guys can go through and read through those slowly and kind of understand everything. It's very basic concepts here. In light of we've done, this isn't going to be the toughest thing for you to actually fit, but with a little bit of time, things will sink in and it'll get a little bit to process. However, once you go to a higher dimension, you're in 3 dimensions or higher, being able to think in terms of parametric equations is going to become more and more. If you don't have the basics down, you are going to be dead in the water. So yes, more fun to deal with. I'll kind of give you a preview of what that kind of thinking would look like later on in the course when we get into 3D and vector stuff. But for now, these are the basics of parametric equations, what they are, how you can plot them, how you can talk about calculus with them, the second derivative, finding tangent lines to approximate the curves, etc. And how to go from a scalar version to a parametric version. This is called parameterization or parameterizing the curve. That's going to be very, very, very super important for vector calculus and a lot of things that depend on vector calculus, which is almost everything in which you're applying calculus, you're going to apply a vector version of calculus because it's better that way for 3 dimensions and higher. Okay, that is it. That is all I wanted to talk about parametric curves. I have no idea what I will be teaching next semester. City College has the habit of not telling you what you're teaching until 1 or 2 weeks before the semester started. It's just how it is. Yeah, I literally found out I was teaching this class like the weekend, the Friday. When did this class start? It started the Friday. It was like 2 days before. So yeah, and a lot of changes were being made last minute. So I don't know. So there were some things that were not included in the syllabus that I think it was a mistake. some of the things about derivatives were not included, but it's actually very important stuff. That being said, our next lecture is going to be on something pretty useful, polar coordinates. We'll deal with those tomorrow, and that will get you caught up with the other class. I'll not cover everything in it. I'll cover some things from conic sections, which I have the notes here prepared for you already as well. Yeah, those are kind of the basics of parametric curves and their calculus. Yeah, no news on the exam. Was I excited or like, for what? Finding out I was teaching Calc 2. I actually wanted to teach Calc 2 because I don't have videos on the new calculus sequence. So the YouTube videos I have were for the old calculus sequence. So I kind of do want to go through the new version of the calculus sequence so that I can have a bunch of YouTube videos. But of course now, because of Corona, that process is kind of getting messed up here. But yeah, I'll ask for, I'll ask to teach Calc 3, definitely speaking, but I don't know for sure if that was the case, so that I can get a new set of videos that are geared towards that. Yeah, I'll let you guys know when I know what I'm teaching. In the meantime, we'll stop there, and I will, yeah, post these notes for you guys. And yeah, we'll stop there for now. You guys can read through it slowly. Let me know if you have any questions, and we can deal with those quickly at the beginning of the next lecture. For the next lecture, we're going to do something pretty different. And we're pretty much going to use the circles. We're going to actually run with this idea and build up a whole new area of math using that, kind of what we did with trig functions. So yes, stay safe. I will see you guys tomorrow. Remember, that's when our next lecture is. And yeah, so cheers and bye, I guess. Goodbye. Have fun, everybody. I'll see you guys in the next one.